So I was going to speak about what we're currently doing with the SPT-3G project, and then what we are planning to do with the forthcoming CMB-S4 project. This is going to blend some of the themes from Benedict's talk on IceCube and then from the last talk on LSST, as we are also straddling this particle physics, astrophysics line, and have some people from both communities. So first, I'll talk about the two experiments themselves. So the first of these is the South Pole Telescope, located cunningly enough at the South Pole. It's designed for precision imaging of the cosmic microwave background with arc-minute angular resolutions. You can see here there's a 10-meter dish looking up at the sky, and it currently has about 16,000 detectors on it. The major way that we've been making improvements in sensitivity for the last 10 years or so in this field has been increasing the number of detector channels in the instrument, and then taking advantage of the corresponding square root n decrease in noise. As I'll talk about a little bit later on, that means that for every factor of 2 improvement in sensitivity, you have a factor of 4 more data, which has been causing some challenges for the field for some time. The current receiver on SPT began science operations in 2018. We take about 1 terabyte of data per day. This is supported by NSF and DOE jointly. Moving forward into the next decade, we have a new project, CMB-S4, that isn't built yet. So we have this pastiche of current CMB experiments, South Pole and Chile. This is a joint Chilean and South Pole experiment. And this is going to have about 30 times the number of channels as SPT-3G. So we're planning on having 500,000 detectors instead of a bit over 10,000. The result of that is that we're going to be taking something more like 50 to 70 terabytes of data per day, which is now a LHC scale computing challenge. And this is part of the factor of 10 increase in data rates every few years, sort of CMB Moore's law, which is starting to become large. This is planned to turn on in the late 2020s, depending on funding availability and various other things, but plus or minus a few years. And we're currently planning the computing architecture for this experiment. So the science that we're doing here is we're mapping CMB temperature fluctuations down to arc-minute scale. This is the smaller scale variation in the cosmic microwave background, measurement of polarization modes and gravitational lensing. We're looking at the beginning of the universe and its whole history, emphasizing earlier times than, say, the Vera Rubin Observatory is doing. And that gives a lot of science. A lot of it is particle physics flavored. Number of types of neutrino, their masses, dark matter, inflation, and then some astrophysics topics thrown in there, looking at high redshift star-forming galaxies, transients, and a few other things. This is what the raw data look like from one of these kinds of instruments. You see a combination of the cosmic microwave background and many other things as you scan the telescope across the sky. Let me see if I can turn my video on. There we go. So as you scan the telescope across the sky, each individual detector records a time stream of its temperature. These are usually superconducting volumetric detectors that are measuring thermal increase between nanokelvins and microkelvins as you move. And this is a combination of the cosmic microwave background and a wide variety of additive and multiplicative effects, including very tiny picoamp scale electronic noise, picovolt scale instabilities in electronics, galactic foregrounds, thermal fluctuations of the focal plane, crosstalk between detectors, ground leakage, annoying solid-state physics that I will not get into in this talk, and a lot of other things. And the major analysis challenge here is to get rid of all of this and leave the cosmic microwave background. When we do this, you filter the data, the raw data that I just showed, for all of these kinds of things as best you can. And then you figure out where each detector was pointing on the sky as you scanned across, what its polarization was. And then the simple version of this is that you just bin those up on the sky and average together every sample from every detector where it was pointing at some particular pixel. This is a map of the sky taken by SPT. You can see the wavy stuff in the background, or cosmic microwave background anisotropies. There are some bright white dots that are largely active galaxies. This is a 10 by 10 degree patch of the sky. CMB-S4 is going to cover more than 100 times as much sky as shown here. One of the interesting things, which I'll talk about a little bit more on the next slide, is that we have the final data products here, unlike a typical particle physics experiment or say LIGO, and more like what Vera Rubin is doing, is that you're using every sample from every detector for all of time while you're observing. And this means that you're doing lots and lots of computing, but there's relatively few computing cycles per byte of data processed. You're not going down to some small subset of data and analyzing the hell out of that. You're spreading this across this very high volume data set. So the key analysis problems that we have in this field are processing these measurements from thousands of detectors as the telescope is scanning, figuring out how to filter out instrumental noise, which can be something as simple as subtracting off a mean, and something as complicated as eigenmode decomposition of a vast number of time streams. And then usually actually what's the dominant part of our computing is doing Monte Carlo simulations to estimate the effect of that data processing on the true sky, which is unknown. So SPT right now is a nice probe of the frontiers here. We're collecting instead about a terabyte of data per day, which is the largest in the field currently by a factor of about 4, and we can't make any cuts. At present, we are usually doing some full suite of data processing per science result, and this is meaning that we're using about 5 to 10 million CPU hours per paper for SPT. Naively, this is scaling with detector count. It's going to be difficult to commit to 30 times that kind of computing load per science result from CMB-S4. So some approaches here. So there are 2 ways to make CMB maps. The simple one is what's called filter and bin map making, where you do the thing that I was describing earlier. You average together all the detectors. When they saw some particular pixel, that corresponds to the value in your map. This only needs a few gigabytes of memory at once. This is what we use for SPT. So you can read in some small range of data, add that to your histogram. This is a just simple data reduction process. And then you can add all of those histograms from all of the pieces of data together and end up with a map of the sky. So we have some software to do this that's architecturally derived from the software used on IceCube. And this reads in about a gigabyte of data at a time. It's embarrassingly parallel because you can take all of your time streams, reduce them into several of these maps of the sky, and then average the maps together. And you can distribute as much as you like. This is a open source Python and C++ project that's currently available on GitHub if anybody's interested. There's an alternative approach called maximum likelihood mapmaking that is much less friendly for the kinds of architectures we're mostly talking about in this meeting. It's called maximum likelihood mapmaking. The filter and bin technique that SPT uses is maximum likelihood if the noise in the detectors is uncorrelated. If you need to include those correlations between detectors, which exist, we spend a lot of time massaging the data to make them small so we can ignore them. Then you need to have all of your data with just petabytes in memory at once, and that pushes you toward very tightly coupled HPC architectures. So we'll get into some of those complications in a minute. For SPT, right now, we have the data are hosted primarily at the Midwest Tier 2 Center at the University of Chicago and distributed using Grid FTP. We're distributing software by CVMFS. This is a repository maintained by the collaboration and also hosted by Midwest Tier 2. So thank you very much to those people. We have this custom software, and then we have some interactive nodes hosted at the University of Chicago that double as submission nodes to OSG, which is where we're doing most of our computing. And this bridges this gap between, the last speaker was talking about, this traditional astronomy mode where you're doing a lot of heavy interactive work, and then the batch processing workflow that we need to handle the kinds of data rates that we have for SPT-3G, never mind CMB-S4. So this is a summary of what we were using last year for our first paper that came out in early 2021 from SPT-3G. We have widely distributed usage, and the users primarily, it's direct submissions from individual scientists rather than the more particle physics standard big production batch queue. And so thank you also to many of the people here. Having access to OSG has made our science possible with SPT-3G. So I'm going to talk about the future. So for CMB-S4, we're having another big leap in data volume, minimum 10 petabytes, probably more from the full survey, probably more like 40 or so. The data are too large to transfer from the South Pole by satellite. We're barely able to squeeze into it with SPT right now, using a variety of lossless and mildly lossy compression. A factor of 10 is just going to blow this out of the water. So we're going to need to do a substantial amount of our data analysis on site at the South Pole. We also have in Chile, this is more complicated than what's being done for SPT. So the existing Chilean science experiments are largely doing these kinds of fancy maximum likelihood things that require tightly coupled computing to handle the large amount of atmospheric noise that's present in Chile compared to the South Pole. It's not totally clear they're required, and that's something we need to evaluate. If they do, it has fairly profound implications for a computing strategy for CMB-S4. We also are picking up, thankfully, not as tight requirements as for LSST, but requirements nonetheless for transient science that will force, in both cases, near live data analysis. This means not a minute, thankfully, but is still sort of hour scale, and it's much more live than we've been used to for the CMB. Cosmic microwave background has been sitting there normally for 13 billion years, so we don't care too much about the data analysis timescale. But transients in the foreground are something we would need to know about quickly. And this is posing some other challenges as well. So the result of this is that we're going to need probably more complex computing architectures, higher throughput, and then deeply heterogeneous. If we have to do these fancy map-making algorithms for Chilean maps that require tightly coupled large computing centers, we're just not going to have that at the South Pole. And so that's going to impose a fundamental shift in how we're thinking of this. There was this discussion in the previous talk about on-premise data centers disappearing. The South Pole will definitely continue having them for the indefinite future. And we have to be able to bridge a variety of different types of computing facility to make this work, including one that's fully isolated. So some lessons that we learned from SPT along the way here are thinking about architecture from the beginning. So this is largely what we're doing right now for CMB-S4. If we design software for one of these computing models and then try to shoehorn it into the other one, it's going to be hard. If somebody writes a data analysis pipeline that requires very large computing centers that are tightly coupled with MPI everywhere, it's just not going to work at the South Pole. Attention to data transfer is also going to be important. Things that we would really like to have, both from experience with SPT and going forward to S4, one of the main things is to figure out ways to instantiate small disconnected compute environments like the South Pole that are similar to big ones. And the last speaker touched on this too, trying to make the on-premises systems look like the cloud ones. I'd also say a lesson we learned from SPT is that requirements for opportunistic H2C computing, which we've been using a lot, more or less match requirements for the small on-site computing clusters. So if we can do that, it's pretty easy. And these other map techniques will be harder. So the current state of the art for CMB-S4 for instrument simulations, which we're working on largely right now, this experiment doesn't exist yet and won't be built for some time. We're using a piece of software called Toast that you can look at if you're curious down here. This is developed primarily by a group at Lawrence Berkeley National Lab. Because this is doing complicated time-evolved atmospheric simulations, it really requires one of these tightly coupled computing environments and large allocations of simultaneously running jobs. We're also currently using the SPT-derived tools for the initial data processing and archiving, either the actual software itself or following the same kinds of design for things that are close to the data acquisition on the instrument. The South Pole live processing that we're doing for S4, we're baselining an SPT-style loosely coupled pipeline. So we have already this fairly heterogeneous effort. Things that we're trying to figure out right now are what we're going to do for the final data processing in the north, which is not the site. Most of the scientists here in the Northern Hemisphere and Chile and the South Pole are both in the south. So one of the big questions is whether we need this maximum likelihood technique that requires tightly coupled systems. If we don't, our life becomes easier. If we do, it's going to require a lot of planning. We don't want to have two completely independent data analysis pipelines that are trying to produce largely similar results. And we have tight latency requirements. This is going to be tricky. We also are going to have this huge data set with varying degrees of availability. One of the things that we've encountered already with SPT, we can't quite send all of our data And that's going to be even more true with CMB-S4. So we're going to need to figure out how to integrate both early arriving South Pole data and late arriving South Pole data, where some things get reanalyzed. We don't want to waste CPU cycles. We want to make sure that happens cleanly. And we don't want to just wait a year either, which has been one of the traditional strategies for dealing with this. You can only, once a year, you have an opportunity to fly crates of hard drives in and out in the summertime. And that's been the go-to data transport strategy for raw data for a while. And then we need to figure out how to store and transport this many petabyte data set effectively. It's very expensive to keep this spinning in a large number of sites. And the central facility is going to require a lot of data transport costs. This is a tricky problem to solve on this scale. And then we're also just going to need a lot of computing. Hopefully we don't need 200 million CPU hours per paper with CMB-S4, because I'm hoping we publish a lot of papers. So we need to figure out how to do a number of things. One is to minimize effort. At present, we've basically been doing an entire separate data processing run for these slightly different requirements for each paper. A major focus has been trying to figure out how to reduce that. Another big issue is to what extent we can use GPUs. Our current pipelines for the whole field are basically exclusively on CPUs. And we haven't had a lot of success with GPUs so far, in large part because for most of our data processing, there's a relatively small cycle count to data volume ratio. And so you spend quite a lot of time moving data to and from GPU memory in a way that does not exploit the possible efficiencies on the GPU. There are, I'm sure, ways around this, but something we're going to need to address. And then we also need to figure out where we're going to get this much computing and how this, as everybody here is familiar with, is easy enough if we have one of these loosely coupled workflows. It's much, much harder if we end up needing tightly coupled ones. So these are open questions in current CMB-S4 planning that we need to address soon and that are in progress. So some conclusions here. Right now, there's just a huge amount of science that's available in this field. It's the precision and channel count are increasing with time. Unfortunately, the data volume increases as the square of the amount of precision. So we have rapidly increasing computational demands as this field is scaling up. We have a successful pipeline largely using OSG for computing from SPT-3G, published data, the best results in the field right now on a number of topics. But going forward to CMB-S4, which is not that far off, where first light is under 10 years away, probably more like 7. We're having this massive increase in data volume and tighter requirements, both in terms of higher precision in data analysis to come with the decreased statistical errors, and then also these time domain requirements and trying to handle the somewhat different data from Chile and the South Pole at the same time. So we need to think a lot harder than we have so far about what we really need. We've been able to kind of scrape by with opportunistic compute cycles, and we haven't really needed to worry too much about accelerators and these other things so far. But now, where we're scrounging for every single cycle of computing that we're going to be using, these things become very important. So that's the end of what I had to say. Basically,
okay,
today,
I was gonna give you
as
like
a conclusion. We have a lot of interesting problems ahead to deal with for CMB-S4, dealing with this interesting data set that's huge volume and small numbers of computing cycles per byte. And that's the end.
Thanks, Nathan. I was just gonna give you the 1 minute warning, but you're right on time. Are there any questions for Nathan in regards to? Yeah, Miron has his hand up. Miron, please go ahead.
Yeah, thank you, Nathan, for your talk and for the challenges that you are presenting. I think that there may be an opportunity for us to help you or to contribute to your, what I would refer distributed computing challenges, when you have to push more capacity closer to the, to the telescope or to the different side. So I would be happy to have some kind of a dialogue to see if there is anything from our end that we can bring to the table that can help you, because that's what we have been doing for a living. is pulling together small sites to create something bigger. And one of this is the Open Science Pool. So if you are interested, I would welcome an opportunity to do that.
That would be fantastic. And it's something that we've been, we're almost at the point where we need to start thinking seriously about how to arrange this in terms of project planning. So now is the time to really welcome the help.
So the door is open, and you know, we can see if there's anything we can do to help you out with that.
Yeah.
Okay.
Thanks.
Thank you for the Miran. Any other questions for excuse me? Any other questions for Nathan before we proceed to our last talk for the session?